we're trying to use some fundamental things that I've been teaching you that are not all in the book, but are related to things in the book. First of all, if you've got a linear system of differential equations, dy dt equals a times y of 0 equals y naught. What I call the beautiful generalization is that the solution, written in function notation with a capital phi, emphasizing what the initial condition is, y naught, as a function of time, is found by doing the matrix exponential e to the ta times y naught. But then that begs a question, how do you find the matrix exponentials? So far to this point, we've always used technology. And what I've told you just now, if you're trusting me on this, is that if you've diagonalized A, if you've written A as P times D times P inverse, where D is a diagonal matrix, this is not always possible to do, and that's actually a big theme on the homework coming up tomorrow and over the weekend, is not all matrices are diagonalizable. We'll talk about that in a few minutes. If you can do this, then you can prove that e to the ta is, in fact, p e to the td times p inverse. And when d is diagonal, this is easy to figure out right there. It's going to be another diagonal matrix with the entries of d being coefficients of t in exponential functions on the main diagonal. Let's go ahead and use Mathematica to confirm or to simplify what we get here. You did this by hand. Fun, fun, fun. If you were doing it from scratch by hand, you have to figure out what the matrix P is. So you have to find the eigenvalues and the eigenvectors of A. That can be done all at once in Mathematica with Eigensystem. This is telling us the eigenvalues are -3 and 2, and corresponding eigenvectors are 1, 1 for -3 and 11, 6 for 2. You put those vectors, those eigenvectors, in a matrix that we've been calling P. P does end up being a change of coordinates matrix or a change of basis, though we don't have to talk about that really in depth today. What's the inverse of P? It's that. Now let's do the calculation. Well, first you might want to confirm that P inverse of P times A times P is diagonal. Get the diagonal matrix by putting P inverse on the left. Yep, there it is. There's our diagonal matrix. I'm going to use a lowercase d for that matrix, because if I use capital D, that's not allowed in Mathematica because that represents derivative. So I use a lowercase d for that. All right, now I'm ready to actually use this formula right here. And you might want to confirm the matrix exponential of D at first as well. Matrix form, matrix exp of T times D. I put a star in there for T times D because T is a scalar. I have to put a dot for matrix multiplication, a period. Yeah, there it is. That's D, or e to the TD, I should say. So now let's do all the multiplications here all at once. Use this equation here. I have to use periods. P dot, this is matrix X. I'll just copy and paste this. Dot inverse of P dot y naught. In the end, this is a vector. You gotta, these things form a, this product is a 2x2 matrix in the end, times a 2x1 column vector. You're going to get a 2x1 column vector. Not simplified. Okay, did you get that? After some pain? Maybe, maybe not. Oh, I see people maybe not getting that. It's okay if you didn't make a mistake, or if you did make a mistake. Let's check that it really did work. We could check it with d-solve value. How? You can use d-solve value with vectors. We could go vector x prime of t comma y prime of t equals the matrix A times the vector x of t, y of t. We've never done this before with d-solve value before like this. Effectively, this is capital Y prime of t equals A times y of t, but I'm putting the components in there. X of 0 equals x0. Well, okay, this, what was it, 4? Y of 0 equals -5. That was our initial condition. Solve for x of t and y of t, with t being the variable, and probably we need to expand it or simplify. I'll try expand. And it looks good. We have a match. Okay, so it is working. I haven't proved why it works, but it is working if you don't make a mistake. What about the difference equation? Y sub n equals A times y sub n minus 1. The initial condition is why not? The beautiful generalization in this case says yn, this is found by iteration of this equation, is a to the n y naught. But that begs the question, how do you find a to the n? Again, if A is diagonalizable, if A equals P D, P inverse for some diagonal matrix D, then you can ultimately say A to the n is this. Actually, that would be true even if D were not diagonal. If this kind of relationship held, even if D were not diagonal, what I just wrote would still be true, but just not so helpful. The reason it's helpful is because when D is diagonal, then D to the n is easy to find. So that's the multiplication you need to do to solve the difference equation. We don't need a matrix exponential. We do need, however, a matrix power. And in Mathematica, this is the way you need to do it. I think that syntax is right. That's the matrix D to the nth power. What does this simplify to? That is kind of complicated, so not surprising if you made a mistake. And this, by the way, Mathematica is writing it in a certain way. It could be written in alternative ways. For example, probably, okay, 2 to the 1 plus n power could be written as 2 times 2 to the n, and 3 times 2 could be written as 6. So this whole thing could be written as 6 times 2 to the n. Would probably be a more common way to write it by hand. 2 to the 3 plus n would be the same as 8 times 2 to the n. So just because Mathematica makes it look this way and you don't get to look this way doesn't mean you did it wrong. Could I use R-solve value to check? Hopefully. I haven't really talked about R-solve value in class. It was in one lecture. Solves difference equations. R stands for recursion or something, recursive. Let's see. We don't want derivatives. We want n's in here. And we want n minus 1s over here. Looks kind of promising from what I can see. Doesn't look exactly the same. There's similarities. Evidently, if we combine these terms involving 2 to the n, it would simplify to that one. Do I believe it? Everything else looks similar enough to make me believe it. Same kind of thing over here. If we combine the 2 to the n terms down here, we evidently get this. And if we combine the 3 to the n terms here and here, we evidently get this. But it's just not written the exact same way. Maybe I should try simplify here. Okay, then expand again. Okay, yeah, that's looking better. Now, it's still not quite, doesn't look quite the same. Oh, yeah, oh, it did something weird there. It used e to the I power. Why did it do that? That's pretty weird. Okay, it didn't really need to do that, and it's doing it again. Okay, for some mysterious reason, Mathematica often defaults to complex numbers and complex representations. It was doing weird things, but I believe these are the same. I suppose we could check it by plugging in a value of n and simplifying that. Take the preceding output and plug in n equals, say, 3 with a decimal to make it round. And then I'll do the same thing here. I'll take the preceding output and plug in n equals 3. Yeah, looks good. So we check it. Percent sign refers to the preceding output. The slash dot and the other stuff ultimately allows me to plug in a value of n into that preceding output. And I'm using a decimal to so that it rounded, but I evidently didn't need to do that. Okay, so it does work. It's a pain, but it does work. Is the book's method superior? Well, it depends on what you've got available, I guess. The benefit of this method is it does relate it to coordinate changes, and that's coming up very soon. It's helping you realize everything in the textbook is related to coordinate changes, is related to linear algebra and coordinate vectors and bases and that kind of stuff. So everything is tied together.